Good morning. Today we're going to talk about 7-5 centers of triangles. Concurrent lines are when three or more lines intersect at a single point. Particularly in triangles. The name of the intersection is called the point of concurrency. And what we'll be looking at today are 4 points of concurrency in particular. So we are going to look at triangles and we are going to break them up into what 3 lines we are talking about. So let's move on to the first set, which are the perpendicular bisectors and angle bisectors. So the first one we are going to look at is the point where the perpendicular bisectors meet. The point of concurrency in this theorem is called the circumcenter. So the point where all 3 perpendicular bisectors meet, and remember, perpendicular bisector means they need to bisect the line or the side of the triangle, and they need to be perpendicular to it. And when that happens, and you do that for all 3 sides, you will get the circumcenters where those 3 lines meet. In this case, the circle is outside, and we've talked about this before. That means it is circumscribed. So the circle is outside of the triangle. The circumscribed point C is equidistant. And remember, that's just a fancy word for meaning equal distances from the vertices. In the triangle. If point C is the circumcenter, then QC is congruent to RC, which is congruent to SC. So the circumcenter of a right triangle is always at the midpoint of the hypotenuse. Okay. And that is an always statement. So if I go back up and look at my triangle, if I look at line SR, this point right here is the midpoint of that line. Let's call that A, which means it breaks that line into 2 parts, 2 equal parts. So as you can see, it has 3 markings on each one. It is also perpendicular. So the line AC is the perpendicular bisector of line SR. Okay, and then if I go over to the next side of the triangle, QR, and I call this point B. B bisects both of those lines, and those lines are, or that line is perpendicular. So CB is perpendicular. And finally, if I go to the third side of the triangle, QS, I'm going to call this point D. So D is the midpoint of line QS. So that line is again the perpendicular bisector. So all of those meet at point C. So what I know is if C is the circumcenter, then all the lines connecting to the outside vertices or the vertices of that triangle are all the same length. So this line is congruent to this line, which is congruent to this line. That is what we know about a circumcenter. Once I find it, I know it is equidistant to all the vertices. So let's move on to the angle bisectors then. So this is where we're going to talk about the angle bisectors. So the point of concurrency of all your angle bisectors is called the incenter. In this case, the circle is inside of the triangle. And remember, we talked about that. That is inscribed. When the circle is inside, it is inscribed. The inscribed point I is equidistant from the sides in the triangle. If point I is the incenter, then what I know is that xi is congruent to zi which is congruent to yi. So if I go back up and look at my picture, so this line right here is the angle bisector for angle T. So it cuts angle T in half. The line UI is the angle bisector for angle U. And IV is the angle bisector for angle V. And what I know, so therefore I have just shown that I is the incenter of the triangle. And if I is the incenter, then this is congruent to this and congruent to that. So these three purple lines are all the same length. So looking at these two theorems, let's try some examples. So if I look at 1, it says find the circumcenter point P given a graph of a triangle or its vertices. So when I see the graph, I can find the circumcenter. So I take the perpendicular bisector. So I'm going to take this horizontal line. It goes from 0 to -4. So halfway in between is -2. And perpendicular to a horizontal line is a vertical line. So I'm going to draw a vertical line at x equals -2. I'm going to do the same thing for the vertical line. I am going to say halfway between 0 and 6 is 3. So I am going to draw a horizontal line at 3. Right there is the point where they meet. I don't need to find the third one because if 2 points meet there, then the third point's going to meet there. So my circumcenter in this case is at the point -2, -3. So if I look at example 2, I can do a right angle test on the angle that is up top. I can get an index card or a piece of paper and just see, is that a right angle? So in this case it is. So I know the perpendicular bisector or the circumcenter is going to meet at the midpoint of the hypotenuse. So in this case, my hypotenuse is this line right here. And halfway between -4 and 4 is 0. So my circumcenter is 0, 0. So first thing I need to do on C, so I can draw it out to figure out where the hypotenuse is, because my circumcenter is going to be the midpoint of the hypotenuse. So if I sketch it out, I have -4, 5, that's at A. B is -2, 5. And C is -2, 2. So where is my hypotenuse? It is the line AC. So I'm going to find the midpoint of AC. So to do that, remember, we just add our x's, divide by 2, add our y's, divide by 2. So it's -4 plus -2 all over 2. And it's 5 plus -2 all over 2. Your midpoint then is, and your circumcenter is at -3, 1.5. Okay, the other way of looking at it is you can find the one that is different. Okay, so if I look at my x coordinates, B is different. If I look at my y coordinates, C is different. So my hypotenuse, because I know all of these are right triangles, is BC. So I can find the midpoint of BC. So it's 7 plus 8 over 2 and 8 plus 4 over 2. So I get the point 7.5, 6. In example 2, it says, given the triangle ABC where D is the incenter, find what is asked. So if I look at question A, and when you have these sort of things, you will want to be able to sketch it out or draw out the parts you need. In this case, I'm just going to use the triangle that's there, and I'm going to erase and come back and do that. So I know D is the incenter. So I know DE, in this case, is 4x minus 1. And DG is 6x minus 5. And I want to find x. Well, if it is an incenter, then all three of these lines are equidistant. So to find x, I'm going to set them equal. So it's 4x minus 1 equals 6x minus 5. Subtract 4x. add 5. So I get x equals 2. B, if df is 2x plus 7, so this is 2x plus 7, and dE is 8x minus 11, find dg. Well, I know they are all equal, so if I find either dE or df, I have found dg. So to find x, again, I'm going to set them equal to each other. So 2x plus 7 equals 8x minus 11. So we subtract 2x, I get 6x. I'm going to add 11, which is 18. So x equals 3. But then I need to find the length. So I'm going to say dg is the same as df. So I'm going to plug it into df. So that's 2 times 3 plus 7. So dg equals 13 units. Okay, looking at number C, or letter C, it says if dg, so dg is x plus 2, and bf is 8, and BD is x plus 5, find DE. So again, we know that DG is the same as DE, which is the same as DF. So this is also x plus 2. So we have a right triangle here that we are going to solve. So here's your right angle. The blue, green, and purple is my right triangle. So I'm going to do Pythagorean theorem. So I'm going to say x plus 2 squared plus 8 squared equals x plus 5 squared. You need to FOIL this one out, so you get x squared plus 4x plus 4. 8 squared is 64. And I need to FOIL this one out as well. I get x squared plus 10x plus 25. Notice I have an x squared on both sides. Those end up canceling each other out. So I'm going to collect like terms. Over here I get 4x plus 68 equals 10x plus 25. So I'm going to subtract 4x from both sides. I'm going to subtract 25. So I get x equals 7.2. But I didn't want to find x, I want to find DE. So we know that DE equals DG, which is 7.2 plus 2. So DE is 9.2. Let's take a look at the last two concurrency theorems. So there are a couple definitions we need to go over before we get to the concurrency theorems. The median of a triangle is a segment whose endpoints are a vertex and the midpoint of the opposite side. So the median connects a midpoint to an endpoint. So the midpoint of one of the sides to a vertex or the point of the triangle on the opposite side. The altitude of a triangle, and we've had this before, is the perpendicular segment from a vertex of the triangle to the line containing the opposite side. So let's take a look at the two theorems that involve medians and altitudes. So the first one I'm going to look at is the point of concurrency of the medians. Remember, this is where you take the midpoint and connect it to a vertex. So the point of concurrency in this theorem is called the centroid. So as a side note, you will need to be able to relate orthocenter are the perpendicular bisectors. Incenter are the angle bisectors. Centroids are the medians. You do need to know that because on the exam it's going to just mention orthocenter and you need to know how all of that relates. So to find a centroid, you find the midpoint of a side. So J is the midpoint of EF, and I connect that point to the opposite vertex. So you find the midpoint, connect it to the opposite point, and you do that for each of the three sides. The centroid point C splits the median into two segments. And the smaller one is half of the larger one. So what does this mean? The smaller one plus the larger one equals the whole line. So in other words, if I think of the smaller as x, and that is half the larger, that means the larger would be 2 of the x's, and that is going to equal your whole length. So you also think of it as smaller plus a larger one are 2 smaller, and that's where I got the 2x equals the whole. The point of concurrency of the altitudes. So just remember, altitudes are the perpendicular lines from the vertex to the opposite side, and we're going to use rulers for this, and you're basically going to use it or an index card because all I need is to be able to do perpendicular lines. So the point of concurrency in this theorem of the altitudes is called the orthocenter. And the segment of the altitude represents a vertical distance on a triangle. It is the triangle's height. That's why we've seen it since middle school. The altitudes are the perpendicular heights. It's what we've always used for the H when we've done area of a triangle. Depending on the type of triangle will depend on where the altitude is located. If you have an acute triangle, your orthocenter will be inside the triangle. If you have a right triangle, the orthocenter is on the triangle. And it's always where the vertical and horizontal lines, or where the two legs of the right triangle meet. And if you have an obtuse triangle, your orthocenter will be outside of the triangle. So, knowing these two theorems, let's take a look at our last couple examples. So, for example 3, triangle ABC and D is the centroid. We're going to find what's asked. So, I know if DZ, so if this whole line is 12, find AD. Well, DZ is the whole, so that means this smaller part, and let's use F because I want to use a letter that's not there, would be F, which means this top half would be 2F. Because you got the smaller and the larger one is twice as big as the smaller. So now I have an equation I can write. I can say AD plus AZ equals DZ. So this is F plus 2F equals 12. So I get 3F equals 12, so F equals 4. And AD was F, so AD equals 4. B, AB equals 6. Okay, so here's AB. So that's 6. So I know AB plus AY is going to equal the whole line, which is BY. I know AB is 6. If AB is 6, then the longer part of that is 2 times 6, which is 12. So AY is 12 equals BY. So BY is 18. And finally, C, if CX is 21, so this whole line is 21. So if I break it into two parts, I know that AC plus AX equals CX. Well, this we already said was 21. So again, I'm going to use some other letters. So I'm going to call the smaller part G. Therefore, this would be 2G. So that is G plus 2G. So I get 3G equals 21. So G equals 7. So if I want AX, that was 2G. So 2 times 7 is 14. Okay, last we are going to find the coordinates of the orthocenter. So first thing I'm going to do is plot the points. So I have 1, 7. I have 1, 2. and I have 11. 1, 2, and I have 11, 2. So we will make our triangle. Please use a ruler. It is very important that we use a ruler to get as straight lines as possible, because we are going to be using those lines along with either a piece of paper, an index card, whatever, to draw your orthocenters. So they must be straight. So we are going to find, in this case, this is a right triangle, right? So the orthocenter, the only one I need to really do for the perpendicular, because my other perpendiculars are there, is the hypotenuse. So I'm going to put my ruler on the hypotenuse, and I'm going to keep it so the bottom is lined up with my bottom, and I'm going to go until I go through the vertex. So we're going to say that is the perpendicular line. Again, on here it's harder to do perpendiculars. So this point right here, let me change colors, is the orthocenter. So in this case, it is 1, 2. So B is a little more difficult because it's not a right triangle, so I'm going to plot my points. I have 6, 10, 2, 2, and 10, 2. So now you're going to take your ruler, and again, you're going to connect them. So we're going to connect a straight line to those points. You're going to use your ruler and connect. Now what you're going to do is you're going to line up the bottom of your ruler on each side. And we are going to make perpendicular lines from the vertex to the opposite side. Perpendicular lines connecting each one to the opposite. So my orthocenter is right here. So it is the point 6, 4. As always, if you have any questions, please let me know.